Summary of lecture 27 about positive definite matrices. So let's dive in right away. So first I just want to remark that this positive definite matrix is still a subset of symmetric matrix. So we are working in a matrix that has this form A, B, B, C. You see they are symmetric, right? And there's a new definition of energy base definition, which is the X transpose as X. And how to use it, I will define in the next section. So that's just simply two simple comments about this and this new definition that is introduced here. And then now, this is an important part right here, that is a task to see if a matrix is a positive definite or not. And this is a critical idea that is introduced here. So let's take an example of this matrix. We have this matrix A, and then I want to test if this A is positive definite or not. And I can go take either one of this, and then it will tell me if it's positive definite. So that's also an important idea. I think that any one of these tasks is decisive. So you can just pick one and then decide if it's positive definite or not. Okay, so first is the pivot test. The pivot test, it simply tells you that it has to be positive. So in this case, the A, pivot test A, has to be positive, and then also the C part, which is the C minus, let's see, we need the factor of B here, and then there's a, no, I think we need to be factored by the A, and then multiply of this one, so B, a factor of B over A, and then this is times the B again, so it's B squared. So this has to be positive. So if you see any one of them is negative, then you know the matrix is not positive definite. And the second one is the most useful one, or the most frequently used one, is that the determinant test. I'm sorry about that, determinant test. So it has also to be positive. And it's not only just the whole determinant. So if you also see in the previous lecture about the symmetric matrix, so we also need to take care of this sub-determinant that is here and here. So for like a 3x3 matrix, you will have to test for the 3 of them. So this 1x1, 2x2, and 3x3. And in this 2x2 example, I have the first one. Let's write it, determinant that here. So the A also has to be positive, and also the determinant, which is the C AC minus B squared, has to be positive as well. So this is the determinant test. And then the eigenvalue, well, you know how to compute eigenvalue. It also has to be positive. So all of this eigenvalue 1 and eigenvalue 2 has to be positive, right? And number 4 is the where we use this energy based definition. So for any vector x, okay, so in this case, of course, the x will be something of x1 and x2 with 2 components. It has to be also positive when the x is not equal to 0. Okay, so in other words, for positive definite matrix S, or in this case we use A, maybe that's better because we use this this matrix, right? So the only case when this is 0 is when the x is 0. So any other than that, if x is not the component of 0, 0, then x will always be positive for if A is positive definite. Okay, so if the only case when this is 0 is when the f is 0, okay, if A is positive definite. Okay, and the last thing, I don't think it's somehow used, it's used by the test, it's somehow more of a properties of them, that if A consists of some columns that are independent, so the A transpose A is also positive definite. Okay. It's kind of confusing here. Let me use a different. Okay, let's just call this S. Okay, and then there you have it. Okay, so you have the positive definite here, and then you want to test it. You check for the energy base, and then if you have some matrix that is of independent columns, then A transpose A will be symmetric positive definite. Yep. Okay. Now that's about the test for positive definite. And there's also this one like a similar thing to the positive definite, which is semi-definite. I will emphasize the word there, semi-definite. And what does it mean is that it's pretty similar to the, especially to this case, this two of this case, the eigenvalues and the energy base definition. But you see, there is a weak inequality there. There is a weak inequality that is allowing you to have an eigenvalue of 0 as well, and also the energy base definition to be 0 as well. So in the case of that, when you have that matrix S which has the eigenvalue of 0, one of the eigenvalue is 0, or some matrix and you test it for a energy and then it brings to the 0, then you know your matrix is a semi-definite. It's not exactly definitely positive, it is semi-definite. Okay, and one other property is that the dependent columns of A, and if you transpose it, A transpose A, it will bring you to the positive semi-definite. So a quick example also mentioned in the book will be a matrix of 1, 2, 0, 0, 1, 2, 0, 0, then you will have 1, 2, 2, 4. So this matrix, you can see immediately that they are singular matrix. This is dependent column, and this is a positive semi-definite, because you know also the one of the eigenvalue of the singular matrix is 0 as well. Okay, so I'll see you in the next part.